Hello, this is Jack Jackson. In this video, I'm going to give a quick review of the overview of basic concepts of inferential statistics. So this is going to be kind of a quick review of the earlier videos in this playlist, trying to make sure we get the big picture for sure, so we make sure we don't lose the forest for the trees here. So let's take a look and see what we've got here. The basic purpose of inferential statistics is to use information from a sample to infer something about the general population. It is to make good data-driven decisions and to quantify a level of confidence in these decisions. There is nothing more important, really, than making our decisions based on real data. Even with real data, sometimes there are legitimate points of discord or differences of opinion on what to do about the facts, but at least we should be able to agree that what the facts say. And hypothesis testing and confidence intervals, which are the two main inferential statistics techniques, allow us to take the feelings out of things and to actually put numbers with these, and we can quantify our level of certainty with this. It's kind of the whole main point of the course. Now, what about confidence intervals? Let's take these one at a time. Confidence intervals provide an interval of values which include the sample statistic, the point estimator. It provides a level of confidence, which we call 1 minus alpha, or the CL, the confidence level, in the interval. The target parameter, for example, the population mean, is fixed. For samples of the same size and confidence level, the confidence intervals will have the same width, but will vary in center. So they'll be moving around. The population parameter, like the mean, is fixed, but the confidence intervals will move around as we do sample to sample to sample. On average, the proportion of them that include the true population parameter is the confidence level. CL, confidence level, equals 1 minus alpha. Confidence intervals depend on three inputs: the sample size, n, which we want to be small, the confidence level, CL, or 1 minus alpha, which we want to be large, and the margin of error, E, which we want to be small. Improving the size of one of these three has a negative impact on one or both of the other two. In practice, we should decide on the confidence level and margin of error that we want in advance, and then determine appropriate sample size before collecting data. In hypothesis tests, what we do is we compare a test statistic from a sample against a known value, or compare two test statistics against each other to determine if it is likely that the sample or samples came from different populations than hypothesized. Hypothesis tests are based on controlling alpha, which is the probability of a type 1 error. In other words, the probability of rejecting the null hypothesis when in fact it is true. The power of a test, 1 minus beta, which can be examined but does not figure directly into a hypothesis test. Beta is the probability of a type 2 error, the probability of failing to reject the null hypothesis when it is actually false. One sample hypothesis test compares a sample statistic against or to a known assumed population parameter. Two sample tests, two independent samples, compare two sample statistics to each other. Remember that before and after data or paired data is dependent to dependent samples, sometimes it's said, is not really two samples at all. It's actually one sample of ordered pairs, and what we do is find the difference in those coordinates, the two elements of the ordered pair, and have a one sample of differences. The null hypothesis, H sub 0, is the status quo. We assume the null hypothesis unless there is a preponderance of evidence to suggest it is unlikely. Population parameter equals some assumed value as part of that null hypothesis. For example, mu equals 50. But in reality, it's a little more than that. It's assuming that we know some particular distribution of sample statistics, like the distribution of X bar values. The alternative hypothesis, H sub A or H sub 1, is what we want to prove. If it's a right-tailed test, the parameter is larger than assumed, is what we want to see if it's true. that would be written something like mu is greater than some number, like mu is greater than 50. If it's left-tailed, we're trying to see if the parameter is smaller than assumed, for example, mu less than 50. But two-tailed test, it just want to see if the parameter is different, larger or smaller than assumed, and that would be a not equal to there. We had two basic approaches for hypothesis tests. The classical critical value approach was to compare a test statistic to a critical value. For example, to compare two z-scores or two t-scores. A t-score to a critical value, for example. Critical values are boundaries of the critical region. The critical region has probability, that is area under the PDF curve, of alpha. I've been shading those red in my videos. Reject the null hypothesis if the test statistic is in the critical region. We fail to reject the null hypothesis if a test statistic is in the non-critical region. My preferred method is actually the p-value approach. In this one, we compare probabilities, compare the p-value directly to the alpha value. The alpha is the threshold for the maximum acceptable probability of a type 1 error, and the p-value is the probability of getting the sample statistic or something as extreme or more extreme than the one actually obtained from the sample that we have. So the p-value is the probability of a type 1 error if we only rejected the null hypothesis for values what we got or something more extreme. That would be what the p-value is. So one more time, it's very important, if you don't remember anything else, remember what a p-value is. It's the probability of getting an actual test statistic that we have or something more extreme given that the null hypothesis is true. How about hypothesis test and confidence intervals? Well, we should use them together. They're much stronger if we use both of them together. Particularly this is true when the conclusion of the hypothesis test results in rejecting the null hypothesis in favor of the alternative hypothesis. We have concluded that the hypothesized population parameter is wrong. We should then include a confidence interval estimate of where the actual population parameter is located. Use the same alpha value for both the test and the interval. Z-test and Z-intervals were used to derive and explain the basic concepts of hypothesis test in these notes and in these videos for both hypothesis test and confidence intervals, mainly just because they were easiest to explain what was going on at the beginning, but they are actually inappropriate in most real-world situations because they require you to know the population standard deviation, which is usually not known, particularly in a confidence interval setting. T-tests and T-intervals are much more often used, or should be much more often used, when working with means. Z and T-tests and Z and T-intervals are concerned about inferences about means from distributions where the sample means are distributed approximately normally. We will examine tests of proportions and variances starting with our next video probably, and the basic concepts from this section and this video still apply there as well, with just some appropriate adjustments of the distributions and the formulas.